A very good morning, students. Today we'll be learning about heat budget. From the foregoing discussion, it becomes clear that the Earth has been continuously receiving solar energy. Most of it is received at the Earth's surface in the form of short-wave solar radiation, where it is converted into heat by the process of absorption. It is also true that through long-wave terrestrial radiation, the Earth sends the same amount of energy back into space, except for a small amount of energy stored as fossil fuels. The Earth atmosphere system receives on an average 0.3 calorie of heat per square centimeter per minute. But the most interesting thing is that there exists a balance between the amount of incoming solar radiation and the amount of terrestrial radiation returned to the space. In the absence of such a balance, the Earth would be getting progressively colder or progressively warmer. This balance between the amounts of insolation received from the sun and the outgoing terrestrial radiation is known as the Earth's heat budget. The figure diagrammatically illustrates the balance by presuming 100 units to represent the total amount of incoming solar radiation received at the outer boundary of our atmosphere. This exchange of energy between the Earth and the sun is made possible by the complex process of radiation. That is why the mean temperature of the Earth remains constant without any substantial variation whatsoever. On the right side of the figure, the details of the incoming solar radiation, and on the left side, the details of the outgoing terrestrial radiation have been represented. What is to be kept in mind is that the energy statistics used in the Earth's heat budget are all based on estimates. And secondly, the calculations made in this regard by different scientists may also differ slightly from one another. Keeping in view the complexity of the process of exchange of heat between the Earth and the various layers of the atmosphere, such a difference in calculations seem to be quite natural. Of the total of 100 units of solar radiation reaching the outer atmosphere, about 34 units are returned to space without heating the atmosphere. Of the total 34 units returned to the space, 25 units are reflected to the space by the clouds, 2 units are directly reflected to the space by the Earth's land-sea surface, and 7 units are scattered by the molecules of air and fine dust. Of the remaining 66 units, 19 units are absorbed within the atmosphere, 17 units by the gas in the atmosphere and 2 units by the clouds. The remaining 47 units are transmitted through the atmosphere and absorbed at the land-sea surface, out of which 19 units are received at the surface as direct sunlight, 23 units as diffused radiation through the clouds, and 5 units as scattered radiation. The incoming solar radiation absorbed directly by the Earth's land-sea surface forms the largest percentage of the total solar energy intercepted by the entire Earth atmosphere system. In all, 66 units absorbed by the atmosphere and the Earth's surface becoming effective in heating the atmosphere. Obviously, the atmosphere gets a larger part of its heat only indirectly. The fact that the atmosphere is heated mainly from below is of great climatic significance, since factors like the amount of cloudiness and contrast in the reflective power of different land surfaces are characterized by temporal and regional variations. The amount of radiant energy absorbed at the Earth's surface shows great temporal and spatial variations. Besides, the land water surface serves as a great heat reservoir because large amount of incident solar radiation is absorbed and stored there to be released consequently to the atmosphere. If all the solar energy absorbed at the Earth's surface were re-radiated directly back to the space, the terrestrial heat budget would be a simple affair. But the matter is complicated. The Earth's surface radiates as a black body since it absorbs and radiates with nearly 100% efficiency for its temperatures. Gases, on the contrary, are selective absorbers and radiators. Thus, the atmosphere, which is nearly transparent to certain wavelengths of the radiation, is nearly opaque to visible light. However, in long-wave terrestrial radiation, the radiant energy from the Earth that is absorbed by the atmosphere is re-radiated mainly upward and downward. If the Earth is warmer than the overlying atmosphere, the atmosphere will receive more terrestrial radiation than it emits. However, there are occasions when a large portion of the atmosphere is found to be warmer than the ground, and in such a case, the net radiation is downward. This is in addition to and at different wavelength from the radiation coming downward from the sun. It is thus because of the greenhouse gas effect of the atmosphere as well as the interplay of radiation between the surface of the Earth and the atmosphere that the Earth's land-sea surface radiates more than it receives from the sun. But actually, this is but natural in the view of the complex streams of up and down radiation involved in the atmosphere. Greenhouse effect. It has already been noted that 66 units of the incoming solar radiation received at the outer margin of the atmosphere is absorbed either by the atmosphere or the Earth's land sea surface. Latitudinal heat balance. While discussing the terrestrial heat budget, it was made clear that the amount of incoming solar radiation is almost equal to the amount of outgoing Earth radiation for the Earth as a whole. But when we consider the heat budget of the different latitudes, it is found that the terrestrial heat balance does not hold good for each latitude. In fact, there is a great imbalance between the different parts of the Earth and the atmosphere, as can be seen. Pronounced excess of incoming over outgoing radiation in the low latitudes and a marked deficit in the high latitudes. Mean latitudinal distribution of the Earth's radiation budget. In other words, at latitudes below 40 degrees, the total amount of solar radiation received at the surface far exceeds the total amount of radiation lost to the space by the Earth. In case of higher latitudes, the situation is reversed, for in these latitudes, more heat is lost through radiation than is received. But despite the fact, neither the tropics are getting progressively warmer nor are the polar regions getting progressively colder. In view of the imbalance at high and low latitudes, it may look strange. But one must not lose the sight of a continuous large-scale transfer of heat from the tropics to the high latitudes. This is achieved mostly by atmospheric and oceanic circulations. It may be noted that the most of the heat transfer takes place across the middle latitude region lying between the latitudes 30 degree and 50 degree. Nature has provided a mechanism of heat transfer from the tropics towards the poles in the form of middle latitude storms. According to one estimate, about 75% of the heat transfer is carried out by atmospheric circulation and the remaining 25% by the ocean currents. In fact, it is latitudinal imbalance of the heat that drives the wind and ocean currents. It is only through the transfer of heat by the winds and oceanic circulations that the latitudinal imbalances of energy are equalized and the heat balance in the various latitudes of the Earth is preserved. Temperature inversion. Temperature decreases with increasing altitudes in the troposphere at an average rate of 6.5 degrees Celsius per 1000 meters, the normal lapse rate. But sometimes this normal trend of decrease of temperature with increasing heights is reversed under special circumstances, that is, temperature increases upward up to a few kilometers from the Earth's surface. This is called negative lapse rate. Thus, warm air lies over cold air layer. This phenomenon meteorologically is called the inversion of temperature. Such situation may occur near the Earth's surface or at greater heights in the troposphere, but the inversion of temperature near the Earth's surface is of very short duration because the radiation of the heat from the Earth's surface during the daytime warms up the cold air layer, which soon disappears, and temperature inversion also disappears. On the other hand, upper air temperature inversion lasts for longer duration because the warming of cold air layer aloft through terrestrial radiation takes relatively longer period of hours. Types of temperature inversion. Inversion of temperature occurs in several conditions. Sometimes it occurs at ground surface, while sometimes it occurs at greater heights. Sometimes it is caused in the static atmospheric conditions, while sometimes it occurs due to the horizontal or vertical movement of the air. Thus, temperature inversion is classified into following types on the basis of relative heights from the Earth's surface at which it occurs and the types of air circulation. Firstly, non-advectional inversion, which involves ground or surface inversion or radiation inversion, and the upper air inversion. Then we have the advectional inversion, frontal inversion, the cyclonic inversion, valley inversion due to vertical air movement, surface inversion due to horizontal air movement. Next comes the mechanical inversion, subsidence inversion, and turbulence and convective inversion. Ground surface inversion. Ground surface inversion, also called as the radiation inversion, occurs near the Earth's surface due to radiation mechanism. This is also called as a non-advectional inversion because it occurs in static atmospheric conditions characterized by no movement of air, whether horizontal or vertical. It may be noted that air is never static. Such inversion normally occurs during the long cold winter nights in the snow-covered regions of the middle and high latitudes. In fact, surface inversion is caused due to excessive nocturnal cooling of the ground surface due to rapid rate of loss of heat from the ground through outgoing long-wave terrestrial radiation. Thus, the air coming in contact with the cool ground surface also becomes cold, while the air layer lying above is relatively warm. Consequently, temperature inversion develops because of cold air layer below the warm air layer above. The ground surface inversion occurs under the following conditions. Long winter nights, so that the loss of heat by terrestrial radiation from the ground surface during night may exceed the amount of insolation received from the sun through incoming short-wave electromagnetic radiation waves, and thus the ground surface becomes too cold. Cloudiness and clear sky, so that the loss of heat through terrestrial radiation proceeds more rapidly without any obstruction. Clouds absorb terrestrial radiation and hence retard loss of heat from the Earth's surface. Presence of dry air near the ground surface, so that it may not absorb that much heat radiated from the Earth's surface, as moist air is capable of absorbing much of the radiant heat from the Earth's surface. Slow movement of the air, so that there is no transfer and mixing of the heat in the lower layers of the atmosphere. Snow-covered ground surface, so that there is maximum reflection of incoming solar radiation. Snow, being bad conductor of the heat, retards the flow of heat from the ground surface lying below the snow layers to the lower atmosphere. Upper air inversion. Upper air inversion is of two types: thermal upper air inversion and mechanical upper air inversion. The thermal upper air inversion is caused by the presence of ozone layer lying between the height of 15 to 35 kilometers in the stratosphere. The ozone layer absorbs most of the ultraviolet rays radiated from the sun, and thus the temperatures of this layer become much higher than the air layers lying above and below ozone layer. This inversion occurs only when there is no vertical movement of air, either ascent or descent of the air. The mechanical inversion of the temperatures is caused at higher heights in the atmosphere due to subsidence of air and turbulence and convective mechanism. Advectional inversion. Advectional inversion of temperature is also called as dynamic inversion because it is always caused due to the either horizontal or vertical movements of the air. Strong wind movements and unstable conditions of the atmosphere are prerequisite conditions for advectional inversion of temperature. This type is further divided into three subtypes on the basis of nature of air movements: frontal or cyclonic inversion, valley inversion due to vertical movement of air, and surface inversion due to horizontal movement of air. Frontal or cyclonic inversion is caused in the temperate zones due to temperate cyclones, which are formed due to the convergence of warm westerlies and cold polar winds in the northern hemisphere. The warm air is pushed up by the cold polar air, and the warm air overlies the cold air because it is lighter than the cold air. Thus, the existence of warm air above the cold air below reverses the normal Raps rate. Decrease of temperature with increasing height, and the inversion of temperature occurs. It may be pointed out that contrary to other types of temperature inversion, the inversion layer associated with frontal or cyclonic inversion is always sloping because the Coriolis force causes the boundary zone, the front between the warm westerlies and the cold polar air masses, to become sloppy. It is also interesting to note that the air moisture increases upward in the frontal inversion of temperature, while it decreases upward in other types of temperature inversion. Surface inversion of temperature, which is caused by horizontal movement of air, occurs in several situations. Such inversion is caused when the warm air invades the area of cold air, or cold air moves into the area of warm air because warm air, being lighter, is pushed upward by relatively denser cold air. When the warm air moves, such inversion is called over the continents during winter and over the oceans during the summer. But when the cold air becomes active and invades the areas of warm air, such inversion occurs over the continents during summer, over the oceans during the winter. Such surface inversion occurs generally in the low latitudes. The convergence of cold and warm ocean currents also causes such inversion of temperature. Valley inversion generally occurs in the mountainous valleys due to radiation and vertical movement of the air. This is also called vertical advectional inversion of temperature. The temperature of the upper parts of the valleys in the mountainous areas become exceedingly low during winter nights because of the rapid rate of loss of heat from the surface through terrestrial radiation. Consequently, the air coming in contact with the cool surface also becomes cool. On the other hand, the temperature of the valley floor does not fall considerably because of comparatively low rate of loss of heat through terrestrial radiation. Thus, the air remains warmer than the air aloft, and hence the warm and light air of the valley floor is pushed upward by the descending cold and heavier air of the upper part of the valley. Thus, there is warm air aloft and cold air in the valley floor, and inversion of temperature is caused. This situation is responsible for severe frost in the valley floors, causing great damage to fruit orchards and vegetables and agricultural crops, whereas the upper parts of the valleys are free from frost. This is why the valley floors are avoided for human settlements, while the upper parts are inhabited in the mountainous valleys of the middle latitudes. Significance of the temperature inversion. Though inversion of temperature denotes local and temporary conditions of atmosphere, but there are several climatic effects of inversion which are of great significance to man and his economic activities. Fog is formed due to the situation of warm air above and cold air below, because the warm air is cooled from below, and resultant condensation causes the formation of tiny droplets around suspended dust particles and smokes during winter nights. The smokes coming out of houses and chimneys intensify fogs and become responsible for the occurrence of urban smogs. Inversion of temperature causes frost when the condensation of warm air due to the cooling by cold air below occurs at temperature below freezing point. Frost is definitely economically unfavorable weather phenomenon, mainly for the crops, because fruit orchards and several agricultural crops such as potatoes, tomatoes, peas, etc. are totally damaged overnight. There are frequent cases of destruction of fruit orchards in the lower parts of the valley due to severe frost caused by inversion of temperature in California. Inversion of temperature causes atmospheric stability, which stops upward ascent and downward descent movements of the air. The atmospheric stability discourages rainfall and favors dry conditions. The inversion of temperature caused by the subsidence of air resulting into anticyclonic conditions increases aridity. This is why the western parts of the continent situated between 20 to 30 degree latitudes and characterized by anticyclonic conditions represent most widespread tropical deserts of the world. In this chapter, we have learned about the heat budget, how the terrestrial versus the incoming solar radiation are balanced out, and then we dealt about the temperature inversion, differentiating between the normal lapse rate and the inversion of temperature. Thank you and have a nice day.